Okay, so it's time to start then next lecture. It's very related to the lecture 5 that we explained on discrete optimal planning. But now we are going to do a very brief introduction to continuous optimal planning. Okay, and well, we'll see what are the similarities, because remember that we approach this problem always from the discrete definition, right? We have a discrete set of states. We did planning there, then we explain optimality, policies, and, well, in general, dynamic programming for solving this. But for continuous spaces, we don't have the same tools, right? But still, there's going to be a lot of similarities. Let's see. So if you want to go and read a little bit more, you have like these chapters in the book. The topics today, we are going to cover a little bit about vector fields, continuous feedback-based planning, navigation functions, but now in this case in continuous spaces, and many other related topics. You will see that it's always going to be, we always try to bring to explain the relation with what we explain on discrete optimal planning, because this is the easiest starting point. But at the end, we'll see that the last topic is just purely optimization, right? So this is a second way of solving the problem, maybe more involved, computationally involved, I mean. But, well, just for you to know that on continuous spaces, there's not a unique solution. We start with this one because from the point of view of the concepts we have explained, is the most natural one. But on continuous, let's say that on continuous spaces, things are still a little bit more open, right? Okay, so for this, we need to explain what a vector field is. On this last lecture, we were discussing about optimality, but it was somehow also a feedback plan, right? A discrete feedback plan. So if you think about it, there was a policy that we were giving state, the current state, and this function, the only thing it was doing, it was mapping what is the optimal action to take, right? So policies were just this, mapping to actions. Now what we have here is, this is a discrete state, but what if we just, instead of being this a discrete element of a set, why don't we say that this could be a continuous element? For instance, well, I don't know, you know about mechanism now. For R, it's not a discrete. We didn't do a discretization of all the joints because that requires like monstrous number of states. But what we did instead is working with continuous values, right? With this, I'm not saying that we will be using sampling. Actually, we will not. But what I mean is that this same idea is very powerful. Feedback-based plan is a very powerful idea. You just have your state, you don't think, you just apply your function, right? So this is one of the great advantages of this. Maybe some of you have already started working with learning-based approaches for planning and all this. Most of them are just an approximation of this policy function. Policies or variants of policies, okay? Some of them approximate value functions, optimal value, but at the end, this is the function that is very convenient for us. To just give some input, and it tells you what to do all the time. And if we follow the guarantees, we know that this is going to be optimal, right, for the discrete case. So this was like most important outcome from previous lecture. From this one, you'll see that we will not have the same kind of guarantees, right, on the optimality, but at least it could be a good thing for us to aim just to have this sort of feedback plan, okay? So for this, we need to just do a step back and talk about more basic concept, that is this vector field. Informally, presenting a vector field means that at every point, right, in this case it could be state space, this case, it's discretized, but it could be a continuous, whatever you want to consider here, this plane, any other higher dimensional space, it's up to you. But for each point, we are going to define a direction, right? And this is an informal way of presenting it. So what you see here is that we have different examples of this vector field. For instance, this is a constant one, always pointing up, right? So this will be a vector like this that is reproduced everywhere. Each of them could be different, right? So this is what you see on the second vector field, right? All of these directions are pointing to the center, right? So this is just a way of obtaining them. Doesn't really matter. And then on the third one, you see that actually there's some curling happening here. So this is, again, why not? Our vector field might be like this. Maybe this responds to some constraints or some other issue that is happening on the system. What matters for us is that if you define at each of these points in your state space this direction, this is what we are presenting now informally as a vector field. And we'll see that this is going to be very helpful for us, okay? Okay, a little bit more formally, but not much. Now, if you remember on lecture 3, we were defining configuration spaces being a very complicated thing. Let's make things a little bit easier for explaining the vector field, and let's say that what we have as our configuration space is just a standard Cartesian space, right? Rn. Nothing complicated, but this is just for the explanation of this. We have each of our configurations that are just a vector, right? And here we don't have constraints, either if it's rotation or, well, other things that you know that can be present there. So what we do now is at each of these points, at each of these points, there's an n-dimensional space that we are going to call the tangent space. Okay? And informally, we have already presented this. It was this direction, right? But this tangent space is different for each point. So in principle, you have infinite tangent spaces, right? For each state. So once we have this, what we can do then is define this vector field, right? So the only thing that we are doing is redefining this as each vector. Okay, so how I'm defining this? It's a function that assigns to a vector b of every point of x such that this vector belongs to the tangent space. Okay, so this is just more formally what I was saying on the previous slide. We just have all points, and for each of them corresponds this direction. So this direction, you could consider this as the tangent space. And remember that this is only one value of the tangent space, right? Here what we have is a full space, so you could literally have any direction you want. Yes, you have a question?
Why do you call it tangent?
This nomenclature comes from differential geometry. So mathematicians have worked with this for a long time, and it's just a way of naming these these kind of spaces around a point. Intuitively, what you need to imagine is this is your state space. Okay, let's say that this is some sort of manifold or whatever embedded in whatever dimension you want. Okay, you have this. Okay, and then locally, what we can define is this tangent space. So we know what the tangent is of a line, right? But now if this is a curve, okay, let's do 2D, okay? Something like this. So this is kind of the tangent around this curve. So if you assume that this is a space, right? This curve could be like different depending on what you want. This is a little bit the meaning, I guess, right? Why they start talking. It doesn't mean that it's tangent, but the only thing that you know for sure is that this space exists only at one point. And then on the, if you want neighboring point, it's going to be a different tangent space that depends on whatever properties of your state space or other things. Now, because we are in Rn, we don't have really this curve thing, we don't have any structure, we just have vectors. It's a little less maybe intuitive what tangent is, but the moment that you start having constraints, like creating curves or surfaces, that's why tangent, the idea of tangent, I guess, comes into play. Right? So this is a more informal way of me presenting it. Okay, very good. Again, so we need mathematical elements, but it's not that this class is about mathematics. We are presenting this in a very informal way, right? Talking about concepts, and maybe for this you have a full course. But what we want is to say that there's going to be then the vector field, and a way to express it is just with the tangent space. Okay, so in our early definition, what we are going to be doing is these vector fields, we are going to use them as velocity fields. And now what we are doing is this thing that look a little abstract, right? So what is this tangent? We start giving them dimensions. So now we start talking about velocities. You will see in a moment what it means, right? So this is just interpretation. There's many other ways of defining this. But you could see this as a velocity field. So imagine, before we start with the equations, you have a lot of particles moving around. Each of them has a position, okay? So you could be saying that your state is a position. Okay, let's do it this way. I have here a lot of particles, right? All these particles. And they are moving, right? So let's say that each of them has a velocity, right? So let's say that these things are kind of curling. So this is a good way for us to define more characteristics about this system, right? So okay, maybe the right way is to augment the state space, but if we have a state space that is only position, then you can consider that these velocity fields are indicating velocities of these particles, right? So with this we have more information. We know a little bit more about this. The same happens here, right? Let's say that for each coordinate, if we want to calculate what is the velocity, and we'll see later what it means, right? So in terms of a path, velocity could be also the derivative velocity that you have on a given trajectory. Like, for instance, you're moving here. What is the velocity here? Okay? So this is a little bit the intuition. And what is important today, it's intuition. Okay? Around this kind of trajectory or sequence of state variables, we can define velocity fields simply as the derivative over time. Okay? So we do this, we just derive over time. So imagine you can do here finite difference, take two elements, do derivation. This is the easiest derivation, or maybe you have an analytical solution for your derivation. Doesn't matter. At the end, what you get is a new vector, right, of the same dimension, by the way. So if you had n dimensions on your Cartesian space, you have now n dimensions on velocities, velocity vectors. And that means that you can think about this function as a velocity field. So the only thing we are doing is how these coordinates change over time, and this is the definition of velocity. Okay, there's going to be a limit for us when we explain things, and this is dynamics. So I said at the beginning of the course that we will not get really into dynamics, but this is approaching very, very closely to what dynamics is, and in general what dynamical systems look like. Okay, so this very easy example of, well, we have derivative of our state, and well, what we have is this function that is just taking, in this case, derivative, right? It's just giving us velocities. But maybe there's vector field that is forces, right? And that's what I'm talking about, dynamics, or maybe other things, torques, right, if we are considering joints. Depends a little bit on how we define things. The thing is that these vector fields are going to help us to define a feedback plan. Okay, so Just a little note then about the transition function, a transition equation. If you think about it, this is the simplest way of saying, look, your system could be determined just by velocities, and then how can you calculate a path, right? Okay, so if we start in the continuous domain, what we have here is this transition equation. What we have is the derivative is just going to be a function. It could be the one that we calculated before. Each of the coordinates in your trajectory, it's just the derivative over time. So this could be a velocity. And for today's explanation, we will just talk about velocities. But it could be any other thing. So the moment that you have a state variable that is not positions is a lot of things, then this derivative with respect to time could be any other thing. This is in the continuous domain. Luckily for us, most of the time we'll be working in the discrete domain. So in order to obtain this function, right, that is called the transition function, we need to do something, right? And usually, well, we need to integrate, right? So we need to integrate this equation over some period. And there's several ways of doing this. I'm not going to get into the details, but the good thing about this equation is that it's not considering derivatives at all. So this is what we had. Do you remember in problem set 1? When we say, you apply an action, and you apply an action here, and you have a state, previous state. The result of applying this action into your system resulted in a new state. Okay, so I'm just giving another way of thinking about it, right? So for most of these, for most of the systems, transition functions come from a physical perspective on a continuous domain, and usually this is after integration of this continuous differential equation, right? Yes. U to be a continuous action. Well, here, yes, I didn't include it here, but U could be a time continuous signal. Usually what happens here, and this is some of the approximations, is that you assume that your action is constant for some interval, right? So this will be kind of discretization. When you want to integrate and do things easy, you just approximate this as a constant. But you are right that here you could be adding here U, your action, into the transition equation, and yes, this could be a continuous function as well. Yes. It's harder than to control things this way, but yes. Okay, I don't want to go like into much detail into this, just for you to know that when we talk about transition functions, it usually has a meaning. There's usually a continuous space, there's usually derivatives, but most of the time, especially, we will always try to discretize and work with transition functions. So, well, take this more as a note. Okay, so far we have defined all the elements, right? We have vector fields, now we have the transition equation. We have said that today we will just talk about velocities, but this could be abstracted to any other thing. And now the question is, let's list all the ingredients that we have for continuous feedback planning, right? As always, we start with a continuous state space. So the state space is first requirement we always ask, and in this case, well, it's continuous, right? So this was the topic of today. We are talking about X, but you know that we sometimes call this state space, but actually we can also be referring to this as the configuration space, right? It's simply, state space is more general, configuration space is the result of looking at the mechanism, how it looks like, how it changes when you, well, actuate it, and so on. The other important thing, other second ingredient, is the action space. And here, you will see something that looks familiar, right? So what we are defining is that for each point that belongs to our state space, there's an action that is a velocity. And in kind of a way of bringing together the two concepts that we explained before, we said that this Action space is just the tangent space around each of these points. Why? Because so far we have defined the tangent space as velocities. So what we are saying is that this is action velocity space. Okay, this is just for now. If we were not talking about a tangent space that gives us velocities, then this would not be true. So I'm just putting on today's considerations. It's easy to grasp the idea if we just think about velocities. Yes, termination action. You remember this derivation from last day, right? Without termination action, what was the problem? Yes, without a termination action or absorbing state, what happened? Okay. Exactly. So this kind of virtual entity that we created for doing nothing allowed us to solve any length problem, right? Just because you just stop. So this was, well, Monday, yesterday. Monday. Oof. Time goes by very quickly. Okay. Anyway, this is still valid. So all things we said are still valid. Why? Because if you have an action that is 0, velocity is 0, that's nothing, right? You do nothing. You don't move. Your state remains the same. You have a transition function that the next state is going to be the same state as you are. And in practice, that means that we have a termination state, right? So we are defining the elements, but I just wanted to know that we still have a termination action here. Unbounded time interval. So this is a little maybe tricky. We kind of have infinite times. For some problems, you might be thinking, why do you want infinite time, right? It's something that it's never going to happen, right? You can never observe like some trajectory that is infinite. Well, let's say that this simplifies the derivations at some point, and well, for us, should not worry too much. Why? Because we know that most of the time, if there's a feasible solution, we will find it, and then even though there's infinite time, there's going to be this termination state, right? So, okay, state transition equation. So, for today, just velocities. So imagine now that you just have the derivative. I'm not adding here any u as any action here, because for today it's simpler than this. We just have a position. We derive this over time to see how much it changes, and this is the velocity. So this is going to be our action directly. So it's kind of a simplification of transition function as we were explaining before. Well, this is the transition equation, by the way, with not with states, but actually with derivatives. And then the last element is goal state, right? So if we have all these elements, then we can say that this feedback plan could be considered as a vector field, right? And this is very important, because now what we have is a way that is going to be telling us what is the action to do, or which velocity we should be executing, this one, just by giving the state. And the state is just going to be this, right? So you just do the derivative, and then you have the action that you have to execute. Okay? Okay, well, we'll see if it's so easy as this. So now we need to find this plan, right? We need to find, like, if it's possible to find it or not. There's also going to be this problem of maybe there's not a feasible plan. So remember, when there's obstacles between your goal and your initial state, maybe there's no solution that is going to take you from the initial configuration to the final configuration. So we also need to define this for a time for a continuous trajectory, right? Okay. So what it means, now what we have is a trajectory. This trajectory is not the sequence of elements that we have. You cannot now take, as we did trajectories as traversing a tree, for instance, and then just looking for parents. Now what we have is infinite elements in this trajectory. So we just define this trajectory as some interval, some function. Here it's mapping to elements in the, okay, let me put it this way, where at 0 we have the initial configuration, and then we have things that are happening here, infinite elements, so you know there's density here of all these elements, and at the end the final point on this trajectory is going to be the goal. Okay, so this is our definition of how a plan should look like, right? It's just a continuous line, if you want, just a continuous line in the configuration space. If there exists one, then we can say that yes, our goal is reachable and there exists. And the second definition is, fine, you can have any plan you want, but which one is an optimal plan? Optimal feedback plan. So in addition of being feasible, in addition of possible to, so for instance, this one is not possible, not feasible. In addition of being feasible, you want this to be optimal. And optimality, remember, that depends on how you define your cost function, right? There's many definitions. Maybe you are just looking for fastest solution, in which case here this L function is just looking for time. Maybe you want less effort, right? And then what you have here is summation of all your actions. There's many ways for you to define cost functions. You could be learning this, right? This could be, I don't know, you give some inputs to your network and then it's learning what is this, because at the end this is a very complicated function, right? You have a lot of, you might have a potentially large input, so your state variables could be large, and at the end what you want is a single value, R value, right? So sometimes, yes, metric learning is, well, an issue. Anyway, let's assume that you have this function, and then the plan is just going to find this. It's going to find, according to this cost, what is the plan that minimizes this cost over the trajectory. Okay, now let's get into, so far we have just talked about general things, right? The key concepts, and now we are going to be discussing about more practical things, things that you might find useful later for implementing continuous feedback-based planning and optimization, okay? So just to sum up, we have talked about vector fields, tangent spaces as it was related, and then all the previous elements from planning, right? State space, and getting a goal. Now we'll see how we can use them. The first example is with navigation functions. So if you remember, on lecture 5, we defined navigation functions as this operator, right, that was looking always for the best action to take, and this resulted in a plan that got in a successful plan, right? We know that, okay, let me write it because maybe this arc mean of this, and then what we had here is L plus the optimal cost to go function, and here we have the transition, right? This is basically what we had. If we find, in this case, we were calculating this with value iteration, but if we have another, not a G-optimal function, but another function, I don't know, B, that was calculated in some other way, and still with this we produced paths that were feasible, we call this a navigation function. And if this was optimal, then we call this an optimal navigation function, but this was referring to discrete spaces. Now the question that we are asking is the same thing for continuous spaces? And remember here that we don't have value iteration, so value iteration it's only for when we have discrete elements, discrete spaces. Can we define the same thing? Maybe there's some function, and here, well, we call this function, but in fact this is a table. So you will see when you implement value iteration that you don't need to approximate this. What you need to put is values of all your state variables to all states corresponding to their values. Okay? But where is this in a continuous space? You have infinite elements. Forget about the table. It's not going to work. So that's the question. That's the question. So far, we have just discussed about things to get here. What can we do in continuous spaces? Okay, so this basically brings us to the definition of potential function, right? We must convert this potential function. We also discussed a little bit about potential functions in lecture 5. We are going to convert it into a vector field such that for every state there is an action, right? And this is very important because before this X was not a continuous space. It was a discrete space. We had a table for this. We just need to check the table. We just need to execute things. And that's not anymore the case. We just have a function here that is mapping from this state to a value, whatever value it is, right? So then the question is, with all these elements that we have, what can we do to find a valid solution? And the answer for this is actually, yes, there are some functions that map states into real values. We still didn't decide which ones. But the interesting thing is that if we want to execute an equivalent optimal action as we had defined previously in discrete spaces, one of the things we need to do is just follow the gradient, right? So we follow the gradient of the potential. I still didn't discuss how to obtain this function, okay? So I'm just assuming that there's a function like this, right? I didn't say how to calculate this. But if there is, and if this function allows us to calculate a path, then the action that we can take is very simple. We just need to follow the potential field, right? And this is called an artificial potential field. This is a very powerful technique if you think about it, right? What we are doing is ideally approximating this continuous cost-to-go function. Now we have infinite elements. We are approximating it still, we don't know how, right? But make sure that, yes, there's a way for it to define this. And then this artificial potential field is giving us this feedback plan that we want. You can think about it also as some sort of vector field, right? So this is just a derivative of the potential in this case with respect to each of the coordinates. And this is giving us a policy. It's not optimal, right? But well, we will discuss later. Maybe we find a way of finding this optimal. But the only thing we need to do is just follow the gradient, right? Just follow the gradient, and we know that it's going to optimize. And if it optimizes, well, let's say that if we have defined it, if we have designed it the right way, we should have guarantees of getting to the goal. But this design is complicated, so I'm going to get into this. Okay, this is an important slide. Everyone here should be on board. If there's maybe something we need to retake, we'll do this. But I have defined all these elements now in continuous spaces. All these vector fields kind of motivate the existence of the potential derivatives just to get to this equation here. Okay. Now our policy is just the derivative of this vector of this potential that we are deriving with respect to the direction. Okay. Okay. What is the idea of these potential fields, right? So they are borrowed from physics. Why do they work? Well, it's basically that some systems just follow these kind of principles. A very easy one is potential, right? So you just have potential. This is done in high school. You know that the resultant force is just the derivative of this, right? So in this case, we can calculate force, but, well, today we were talking about velocities. Still, we will not talk about dynamics, but this was the first motivation for people to study this. If there's a way to define this potential and then we just need to follow the derivative, why not? Let's try to design these potentials. Ideally, we want them to be optimal. But if they are not optimal, it's okay, right? Why? Because it's a very powerful concept once we have this function defined, that the policy is just going to be following the derivative. Very simple. The plan is here. The plan. This is a plan. If your potential is correct, you should get feasible plans on all the state variables. Okay, so I hope now I have convinced you that this could be like a way for us to work into continuous spaces. I don't have more alternatives for now. Maybe we can discuss this so you know what happens when you have infinite elements. We cannot really search over them, even if it's very efficient. We can discretize them. We can discretize them with sampling. This is the other alternative, right? So we already did this. But in this case, we are directly tackling the problem just by saying, okay, fine, there's no need for us to calculate all elements in this continuous space, but we will follow derivatives, right? So this is another extra thing that we could be doing. Okay, so let's give an example. The problem with this, and this is the key thing, and I'm sure that almost all of you are thinking, sure, but what if you don't have this potential field? Then all this explanation is for nothing, right? You could just say, yeah, sure, your potential field is 0, and we know that this will never solve any plan, right? So not all potential fields are good. That's the other little problem, dirty thing, or hidden secret about this, right? Defining them sometimes can be very complicated, and we'll see that there's little issues about this. Let's start with very, very simple one. If you remember, all of them were pointing to a position. Let's say that this position, why not? It's our goal. It should be the other way around, right? You first define the goal, and then you might have this potential build. So in this example, I'm just proposing this potential. Why not? The only thing we are doing is squaring each of these components, right? So the farther away you are, the higher the potential is. And then what we see is that if you do the derivative of this, you follow the gradient, it's just going to be this, minus x, x1, minus x2. So these are all these arrows that we were plotting before, right? You can imagine this as this vector field or kind of action space for all your states. This also is not a discrete representation. You could be plotting here infinite arrows if you want. It doesn't matter. You just need to check where you are here, and this is giving you automatically the velocity. Okay, so this is what, again, the term of policy comes like very in hand. You just have your state, you just execute your policy, and then, well, this is the action for you to execute. Okay, how to calculate this? Well, there's no need to do derivative, right? But you see that you get this, and then you get the other one with respect to the other. Okay, still, we need to design these potential functions, right? And no one is giving us any guarantee that it's going to work. But for this case, for this kind of open space region, this works. Any initial point, any initial configuration, it's going to result, if we follow this policy, into achieving the goal. Okay? Okay, probably it's not, well, kind of a little side note, but there's a high relation between this way of thinking about plans as feedback-based plans over derivatives or following gradients or derivative of potentials and controls, right? Again, I'm not going to talk about controls. There's a lot of courses on this. Maybe some of you know. Others, you might have heard about it, right? But this is kind of just, I'm bringing some similarities between the two things that we have defined, because when we get into continuous spaces, the term planning, the term control, especially also if we talk about policies, the things are common on many different fields, right? So we are just talking about things that other disciplines have been studying also, right? So it's studying the same problem. We'll see which elements are in common, right? So this could be, well, let's say that this potential field could be understood as very, very elementary controller, okay? So in this case, what we have is, well, this potential that we were just proposing, why not, this derivative, and the equivalent could be just a proportional controller. So what is this? What we have is an error. In this case, we have this, right? So this could be our error. And the only thing we are doing is multiplying this proportional signal with some number. 1, why not? Okay? These two things provide the same kind of action, right? So we get the same action from controls, and we get the same action if we define this potential field and follow the... remember that this, actually, it's justified because we are minimizing this operator. So locally, what we are doing is always looking for which is the best direction that we should be taking if we want to minimize this function. Okay, so here what I'm doing is also discussing about our findings in dynamic programming, and we know that this local operator in discrete spaces, once we have converged, is going to take us to the goal, guaranteed, 100%. You will see in problem set 3, by the way. So this is a strong guarantee that we have in discrete spaces, but we can still have sort of notion. There's no guarantee, but at least the same idea applied to continuous spaces. And, well, this is where we are here. Okay? So controls does the same thing. It's not talking about optimal cost to go function or whatever. It's just saying, look, you have an error, and you want to minimize the error. But at the end, this very simple approach results in the equivalent thing. The explanation about this requires more elaboration, requires talking about vector fields, however, and many other things, and optimality. This one is, okay, just reduce the error, okay? Controls does a lot of other things, right? So optimality is also an issue here, and again, I'm not really going to go like a lot into this, but just for you to know that these things sound familiar because they are solving the same problem. Okay, now, how can we define this potential field, right? This example was correct if we have an empty space. If you have an empty space, you have a goal, you could be doing something like this distance to the goal if you want, so this could be your potential. Wait. This is a distance of x and x goal, right? If you want to think about it. No, this actually is this square, right? So it's kind of saying, look, your potential is just distance. You want to minimize this distance. This is a way of defining a potential. There's many others. Maybe it's not quadratic function, but you want to use another thing. Now, the interesting thing is for empty spaces, I think it's easy to define potential that is going to take you there. So this sort of kind of distances that all of them kind of grab you to the same goal, these are going to work. These are examples of potential fields that are going to work. Might be optimal or not optimal, doesn't matter. But at the end, you are going to reach your goal, right? And what if we have obstacles? What if we have other things? So this is where composition of potentials comes into play. Right? Can we define a composition of potential functions? This is the question, right? And this is where defining or designing a potential could be a little complicated. Yes. So, as I said, the first one would be an attractive potential, right? So this could be just distance. I mean, this is distance, right? It's just weighted by this. And then this solution is just going to be the derivative of this. So you just do derivative. Okay, and what is the other potential that we could be defining here? We could be defining a repulsive potential. Okay, so the repulsive potential, if there's an attractive one that is taking us always to the goal, maybe there's repulsive that is just doing the opposite, is taking us away. So I'm here now plotting this in 3D, right? So maybe if you come here, you will see that, yes, this potential is just doing this, right? Okay, you need to use your imagination. But yes, the composition will be this. You take these two potentials and you put them together, and this is still a valid potential function, right? Okay, let's do a little break. I said this is a valid potential function, but I didn't say that it's going to be a feasible plan, what we get in result. And we'll comment a little bit more later after a 5-minute break. So let me get back to what we were discussing. The idea was, it's fantastic if you can create a potential. We have then later defined this vector field around this potential for velocities, which is true, and in general would be for any other actions as well, right? But then the question is, yes, but then we have the same problem as we had before. If we cannot calculate this function, then what is this for, right? And then we were arguing that when you have empty space like this, it's very easy to do attractive potentials. So it's just, imagine, more like kind of quadratic things if you want, or basically what you want is, and this is informal kind of way approximating this, but you need to imagine that the potential has like some properties, like always be decreasing and so others. But this kind of bowl center at your goal, you have guarantees that yes, you will find here your plans will always end up in this final configuration. For repulsive, you don't really have this, right? So then what we were saying is, okay, now in this environment, you could be defining an object, and although you have an attractive field, how can you combine this with a repulsive potential field? And the great thing about it is that superposition principle works here. So you could have two potentials, just sum up them, and then get a new potential. So it works like this. You have one that is for sure taking you to your goal, right? Like for instance, in this example, we have here the goal. And then you have a bunch of objects. And then let's just gonna sum up them. Again, this is more kind of a heuristic way of calculating this. If you want to calculate this properly, well, we'll discuss a little bit later. But let's say that at the beginning this was really a thing, because this allowed to solve many problems that were not possible to solve, like very easily and in a fast way. So if your potential is just superposition of all potentials, here imagine what you have is a little bit of repulsive center at each of the objects. So imagine something like this. If you do superposition of this is kind of contour lines on all values that you have here, right? And if you calculate the vector field that we were discussing, what we see is that most of the time you just follow the path, right? You just get to the goal. But when you get close to the obstacle, then there's going to be this repulsion. Okay, so this is not principle at all. We have just defined these functions because we want. There's just kind of physics motivation, but it's not strong guarantees. I'm not saying that this is going to work all the time, but in practice, this is a very fast way for you to calculate a feedback-based continuous action working on continuous spaces. Okay, so looks great, but there's a little issue about this. and which makes these potential fields good, but you need to be very careful when you use them. In practice, you might not want to use them all the time, just when you have very clear idea that things are going to work well. And if you want to use them, still you should have like some contingency plan. Because the main issue, and this is something that has been known for a long time, is although they are very attractive, although they are very easy to use, very powerful, computationally very efficient, this is a great thing. Although all these things, if you define yourself, the potential as we are discussing now, just kind of this attractive, and then you start putting objects, and then the problem is going to be local minima, right? So you could have a feedback-based plan, no doubt, and it's going to work. But if you don't correctly design it, there's going to be local minima, right? And an example is the configuration we had before. We have this thing here. We have this thing here, for instance. And imagine that okay. So let's do this one, okay? So this is probably one that you will say, yeah, but this has never happened in practice. If you're exactly in this axis of symmetry, here you have a repulsion that looks like this. And here you have an attraction that is taking you to the goal, right? So if you come in a perfect straight line, you're going to find a problem that no one is telling you to go to this side, right? If you move slightly, by the way, you are going to find the problem. But can you imagine this? So you are perfectly aligned with the goal. The attractor is telling you just go straight. And the repulsive is telling you don't go straight, just go to the side. Okay, so if you come here, you're going to find a local minima. You can break this just very easily just by moving to this point. So on this point, then repulsion is going to have like some... it's not going to be totally aligned with the attractive, right? This also creates sort of problems, not just because of local minima, but because the velocities around these obstacles are not very optimal. Let's say that they are, well, very small. Let's say that we have another problem, right? I'm sure that now you are thinking, I can solve this. There's ways of overcoming this. Yes, yes, there are. But I'm just giving an example for you to think about, right? So it's great from one side. I'm telling you, you don't need to plan. You just execute your derivative, and that's it. But you need to know what price you are paying. And the second is if you have kind of a strange thing like this, not a convex object, but you have sort of non-convex and larger, there's no way for you to escape this, right? So your potential field, as we have defined it, it's going to take you to this dead zone that you will never escape, right? So if you just follow the gradient, it's great until things start getting a little bit more complicated, right? So for really complicated configurations where you need to think about this, think about going, these kind of techniques are not going to work, okay? So it gives a lot of advantages. I'm not trying now to disappoint you by saying, why have you spent the first hour talking about this? They are still great. Usually this is the first step just to have continuous solutions, right? So you are considering continuous solution that so far it was not possible. The key ingredient, if you remember, it's this local operator, right? So the only thing we are doing is just minimizing this potential field, right? So this is why this is so attractive. We are just taking this potential and doing derivative. Very, very easy. Taking from dynamic programming, right? So there's principle, but it's not exactly the same, because for dynamic programming we know that it was guaranteed. For this one is more a guess. Okay, so local minima, definitely something you always must consider if you want to use these techniques, but if there's not a chance, or you have ways of avoiding this local minima, these kind of approaches are very easy, because literally it doesn't take much computation to think. You don't need to solve RRT for 10 minutes, right? You just follow the policy. Super easy. This, by the way, you will see in problem set 3. So it's not continuous, but it's discrete, but still you will follow the local operator. So you will implement a plan that is just based on following the local operator. Any question here? Comment? Okay, so now let's be a little bit positive, because even though there's many things we can do, right? Even though there's local minima, this kind of techniques is a really powerful one. Right? Okay, in practice, this solution can be calculated real time. So this is what I was talking on, very efficient. You just real time, and you still have a lot of budget for doing other things. If you need to plan every time, think about it. It's like you are considering every time everything. So you are considering the scene, you are calculating a plan, and once you have it, you execute it. This one kind of solves the problem before. First, you calculate your potential. So this is where kind of most of the processing is done, and then later you just follow it. Right? So once you calculate your solution once, you follow it. There's great synergy with learning, and at the end, what you are doing is just learning these functions, right? These policy functions. So it's nothing else. And we know that there's guarantees for this to work. So this comes from dynamic programming. Okay. Local minima, right? Local minima was like kind of the only little problem, but there's two different strategies that people have been doing. So for instance, you can define better potential fields. These ones that I was telling you about, this quadratic plus repulsive, this is the first thing you do, okay? If you want to have a little more guarantees, then you could calculate potentials that actually take into account all these regions, because at the end, what you are going to have is regions in your potential that are not decreasing, right? So that's where you get trapped. Imagine here I'm plotting ISO contours, okay? So if you get here, there's no way for you to escape. There's no one that is going to be telling you here. You are always, all the time, going to come here. So what if you could create some potentials that are nicer, that are well-behaved, that do not allow you to get trapped into local minima? So an example of this is optimal cost to go. This, we know for sure that there's no local minima there. If you take the optimal action, always you're going to have the optimal plan, guaranteed. It's discrete, but okay, little detail. And the second one is harmonic functions. So you could also be creating your potential functions with harmonic functions. I'm not going to explain now what they are, but it's basically a more elaborated way of calculating your potential field. Another very interesting strategy is hierarchical planning. So do you remember first day when I was talking about topology on planning and many alternatives? There was one thing that I was saying, look, you could have your planning here that is kind of inserted into higher, hierarchically higher solution of your plan, right? So in your case here, we could be separating over this low-level plan that is giving us continuous spaces, and this is great. But if you want to look kind of in the future in a coarse way, why don't you just take A star with a very coarse discretization, solve it, and on top of this, you are just running potential field. Okay, so why not? This is just a strategy, but the idea is hierarchical planning, right? You divide the problem such that local minima is not going to appear. You know for sure that your goal is not going to be in a local minima configuration, right? Okay. Yes, explaining a little bit about this, let me talk about cell complex and potential fields. This is just very popular technique some time ago, long time ago, that people, what they were doing is you have a complex cell. Inside this cell, you just run your potential field. Doesn't matter, right? You know for sure you have guarantees that from any point in the cell, you are going to reach the edge. And then the problem is basically how to connect these edges, how to connect these cells such that you get to the final position. So here I'm starting here. I'm just following the arrows, right? And this is discrete okay, this one is coming here, this one is coming here, this one is coming here. This higher level planning could be solved easily with graph-based planning, right? So you just have a bunch of cells and you want to traverse them. You don't need to solve the particular actions that you are taking. You know, you have the guarantees that anywhere that you stay here, you're going to be able to get outside the cell. So if you connect them on the right sequence, your plan will be good. Yes, say. How do you find the potential on each cell? If you have noticed, cells are kind of convex, well, they are simplex in 2D, but they are convex regions inside. So any kind of attractive function will make its job. So we don't need a very complicated potential field. Objects, on the other hand, they are represented just by the correct decomposition. So if you have enough of these cells, you can overcome any problem with objects, right? Goal is here. Yes. No. This is not a constant. Yes, okay, so you are talking about this arrow. This is not a constant. This one? This one? These things? These arrows you are talking about, or which ones? Yes. This one. Look, but this is not exactly the, yes, okay, so you are saying that the resultant trajectory is going to look like very ugly, right? Like this. It's not exactly like this. So if you see there's not a goal in the center here. What you have is a segment. And the segment is the exit segment. So you could be defining this, you could be optimizing this in several ways. One is, yes, you just get to the center if you don't want to complicate your life too much, and in which case things are going to look more clunky, but you could also be optimizing over the segment itself. So you could be just not deciding which segment it is, but exactly where in the segment. And with this, you could be looking for more optimality. So the potential is just a way of defining things. But still, you know that you can exit any part of the edge, right? So if you're worried about these arrows to be, this is just illustrative. This is just for you to show what's going on, okay? This anyway is an example. The thing is, inside, you could be running your potential field thing, if you want. Outside, because there's obstacles you don't know. So what you do is you create more of these kind of guaranteed cells. Okay, another example, funnels. Funnels is this idea that you have a region, and from this region you know for sure, so here I might be including dynamics, I might be including other things, but you know for sure that a small region is reachable, right? So you usually call this kind of your goal. Instead of being a segment now, it could be like small region. And then the good thing about this funnel is you are kind of funneling your plan, okay? So if you create a cover of these funnels, this is covering the full space, with these funnels, at the end you have a guaranteed way of finding your solution. What is happening on each of the funnels? You could think about it as a way of as a potential field, if you want, right? Just taking us to one of the, and then what you need in this higher hierarchical planning is how to connect the funnels, which goal you should be looking for here just to get to the final solution. Okay, so this is another example of how to divide and conquer and solving this, right? So in this case, well, it might look something like this. There's other interesting approaches that you could be doing for this. So you could be defining a tree of funnels or a tree of regions, and this is what LQR tree is doing. Well, basically, let's say that when you have a two-dimensional space, it's very easy to create a cover, but when you have a high-dimensional space, create a cover of the full configuration space is not that easy. So you might want to sample, same as what you did with RRT, right? But imagine instead of having a point, what you have is, one cover of the funnel. Okay, other solutions, cost-to-go function. So we have talked about this before, and everyone, I'm sure, is asking, but why don't we use this? So yes, we can use this, but the problem is we have guarantees for discretization, and we want somehow continuous function, right? So here what we have is a table, and what we want is a continuous function. Okay, so with continuous spaces, where we have infinite number of elements, how can we store and compute this function g? So what we can do is, there's many solutions, right? But we need to use a function approximator. Okay, so here that means that some parameters, maybe thousands of them, maybe a couple of them, are just going to parameterize this function, right? And you are going to be approximating optimal cost-to-go function with this parametric function. It was very popular, by the way, doing function approximator since a long time ago, so people have been using polynomials, ellipsoids, many other things. It's just very recently that people have shifted to neural nets, but it doesn't mean that they invented function approximator, right? It's simply a very expressive way of approximating any function, as complicated as you want, right? So this is giving you this guarantee, and this is kind of a great thing. What you need to do is, well, I'm sure that you have guessed, you still have the Bellman equation, you need to optimize over this, and at the end with these function approximators, the estimation of the optimal cost-to-go function is going to be optimizing over these parameters, right? So we need to rewrite a little bit this equation, the Bellman equation, to include here parameters, but at the end you will get if, remember, this was the Bellman equation, okay? Once we converge into this, we were saying, okay, maybe what we do for convergence is just run many times, and at the end it's going to converge. But if we have now a parametric function, maybe we need another way of looking for convergence. But the truth is, once you have these properties satisfied that converges, you have an optimal cost-to-go function, right? If you have an optimal cost-to-go function now in continuous space, this is great, because the only thing you need to do is just calculate its gradient, right? And then we'll follow the direction. So this could be a policy, very easy to calculate. If you don't want a family of parametric functions, other people have been using, well, before neural nets, I guess, interpolation. So in this case, you discretize, and your cost function is just going to be interpolated from some values, right? Let's say 4 or whatever. And well, basically what you need is a grid structure or other kind of a structure that discretizes, and then, well, you interpolate in between, right? I guess now there's no point on doing any of this, right? Because these approaches have been but every time that you see someone applying any policy, learning, reinforcement learning, all these come from the same idea, right? The only thing you are doing is variation of the optimal cost-to-go function, or maybe Q function, or other function, you are approximating it, right? And well, you're approximating it with many other parameters. So this comes from here, nothing new. You should be aware also of the limitations of cost-to-go functions, so they are very powerful, but you really need convergence. And well, I guess I'm just kind of opening the door, saying that yes, learning is very powerful, but it's based on well-grounded principles some of the time. And I think, yes, sometimes you need to think a little bit about them. Okay, let's do a little change of topic now. I have discussed how can we make it work, how can we calculate feedback-based plans on continuous state spaces. This is great. We have found some guarantees. At the end, we have discussed like some of them that look very powerful, like optimal cost to go. So we can even have optimality here on continuous spaces, funnels, potential fields also. This is a different kind of paradigm. So now what we are saying is, okay, let's forget about all things we discussed about dynamic programming, and let's just solve this like in a proper manner. Okay, and the proper manner is you take a function, a minimization function, you define your state variables, and then you just run optimization, right? Could be nonlinear. Yes, mostly it's going to be nonlinear, but then you just need to define the problem. Once you have this, there's a lot of solvers that take this problem for you and solve it for you, right? So they even handle constraints. Here, these are intervals, and you have here the initial conditions. Okay, so I'm not saying this is better or that this is worse, but some problems are definitely solved like this. You just redefine your problem into an optimization, and then your plan becomes optimizing, right? And for this, there's a lot of solvers, a lot of literature, and well. Okay, the little detail, I'm not going to go like a lot into ways of solving this, constraint optimization and all this, but the only little detail that we need to take into account is that for this to work, there's usually like 3 main approaches, and each of them depends on what we discretize. So we need to discretize something. That's the other problem, right? We cannot just calculate. So how can you? We'll have the same problem, okay? Imagine here, we are minimizing with respect to u of t and q of t. We'll be optimizing with respect to not a discrete set of elements, but kind of a continuous trajectory. This is more complicated, right? So, well, in this case, this will be a functional, but at the end, most of the time, you will need to discretize something. You can even discretize your actions. So say that, I don't know, you have kind of constant actions or something like this, or you could be discretizing your state variables, right? Or, well, kind of combination of both. If we parameterize the trajectory with Qt, right? I mean, this is configuration. We can solve the problem directly for the trajectory, right? So that means that we have okay, so this is U. We have a sequence of configurations, and the only thing we are doing is shifting them, putting them up and down, or right. So this is Q, and when you optimize, you are going to change these configurations over slightly, right, just to make things more optimal. Yes. How can you do this with continuous trajectories? So, because you cannot optimize fully like these continuous spaces, what you do is you do these little shifts just by using this parametric representation, right? So it could be a spline, it could be a polynomial, a Fourier. You basically need to represent this trajectory like this. Here, yes, controls I think yes, then what you will have is discrete controls, right? So these are the variables you are optimizing. Other solution is you parameterize the control signal, okay? So instead of just optimizing for the trajectory, you optimize with respect to controls, but remember that here it matters a lot what you do with, I mean, these controls result in new state spaces, right? So here you can directly optimize for this, but then at the end, because, well, what we have is the transition function or transition equation, whatever you want to use, you're going to have to take this constraint into account, right? So you always need to apply the action into a state, and this propagates into a new state. Okay, so how can we calculate the trajectory? We just integrate these equations of motions. Okay, let's put it this way if you want. Okay, the second thing is you could be parameterizing both the trajectory or you could be parameterizing the n and the action space, right? And the thing is how to satisfy then the transition equations. So this is a little bit complicated. You are parameterizing both things, you are optimizing both things at the same time, but no one is telling you that you are going to ensure that the transition function stays correctly. Okay, so all of it is kind of a little bit the same. We discretize the problem, now with parameters, we optimize over them. Different ways, one is optimizing control and then integrating, the other is with trajectories and then extracting controls, right? From this. Actually, yes, no, it's not. You need to solve the inverse of controls, right? Given a sequence of positions. Anyway, these things you see that have some problems. I'm just presenting them. It was not the main topic of today, but this is the other alternative. Optimization could be done. You just need to adapt your problem, your continuous trajectories and your continuous action spaces. You need to apply them slightly different, and then using optimization techniques is possible. Let me put this in a little bit, well, examples. So some people are also using optimization as inference, and they are solving some of these trajectories like this. So you could think about inference is just a process of optimization. So optimization is in many processes. And you could be using these well-known solvers that are used here. You could be using them directly for your task, that in this case is calculating a plan, and you can see what is happening here. Okay, so you have an initial trajectory that it simply gets optimized. Here, well, people were using factor graphs, maybe some of you know, but this is an inference technique. Gaussian processes are also another way to solve this problem. And at the end, it's a little bit of the same. You are just using techniques that are there for optimization for you to calculate a plan. Imagine here, you don't want to come here. You basically, what you want is a trajectory that doesn't collide with anything. If you keep doing this many, many times, right, you keep optimizing, at the end you will get a plan that satisfies your objectives. Okay, so for today's lecture, at the end, I was talking more about, I was surveying techniques. I didn't explain properly optimization. For this, you have courses. If you have questions, please, I will be happy to discuss, but I didn't want to get like a lot into this topic. For today's class, the most important thing was how to apply navigation functions now to continuous spaces. So we have discussed a lot about this. And we've seen that although there's issues, like local minima mainly, there's also ways for breaking this. If you want ideas for projects, I think now is the time. You have to start doing groups. So maybe it's the time to check some papers in Canvas, talk with us, talk about topics. It's going to be next week's a little bit of open process, right? So write to me, write to TAs, some ideas. It's going to be okay. We can, I think we should be, all of us, discussing about what you want to do. And then when you write the proposal, still we are going to be discussing. But after 6 lectures, 2 problem sets, I think you are ready. You have kind of big picture. Little, it's not finished, so there's still a couple of lectures, but you have a big picture of topics in planning. There's many, many things going on, mostly, well, on research. Let's say that I'm talking about classical methods, but current research approaches include learning, include mixture of planning with other disciplines. So I'm okay with you looking into very new papers, but careful because you need to implement this. Okay, so if you are being over-optimistic, we will cut you down. So, but anyway, the discussion should start from your side and from our side. Okay, thank you.